Hi there. I'm at home today and I am trying to make a video to sort of emulate what we were going to do in class, and I apologize in advance for the for just it having to be on video. But what I wanted to do today in class was talk to you all a little bit more about mining, impacts of mining, so that you have just a little bit more background and understand it better in class. All right. So that's my little preview. Ta-da. So copper extraction is the title of the lesson today, and this is a little example of what sort of processing is needed to extract minerals from ore, as well as an explanation of the ecological impacts of that. But also, what I'm going to talk about is kind of interesting because it's both a process that we use to try to extract the little remnants of things like copper or other minerals that we didn't quite get the first time around and that end up getting dumped out as spoils, right, as that overburden leftovers. But it's also a process that we see happening in natural ecosystems, just simply as a result of the kinds of abiotic and biotic interactions that happen with minerals themselves. So it's a lot of new information to discuss. But what I wanted to preface all of this with is a then and now kind of comparison. Copper, Cu, in the periodic table of elements, copper is a metal and we use it for a lot of things today. Today we use it in electronics, copper wiring. It's excellent at being a conduit. We also have copper in all kinds of different devices, but for both household objects and cookware and jewelry, and just because we like it and it's shiny and a pretty color. We also use it as a fixture for pipes. But in ancient times, people would come across this pure nugget of copper, just straight copper, kind of the same way that they would come across gold. And so, because it's fairly easy to melt down and then reshape into whatever object you want, people would use it for jewelry. They would use copper to make weapons. And after a while, all of the easily accessible pure copper was removed, was picked up, was found, was discovered, and was extracted and processed and utilized. And so what that led to was we need to find copper wherever else it might be found. And copper, being a mineral, is found in rocks. It's found in a lot of different types of rocks, but oftentimes, depending on the type of rock it's found in, there might be other compounds associated with it. So the picture that you have here in the top of the slide is azurite, and it's really kind of a pretty rock by itself. It actually can be polished and used to create little stones for jewelry, earrings, necklaces, whatever. But it has within it copper as well as hydroxides. There's also, I don't think it's calcium, but there's carbonate. So it's kind of mixed in with all of these other things that you're not necessarily interested in getting. And so to extract the copper out of the rock, you need to process it. And I'm going to talk a little bit more about that and how we do that in a lab setting or in a mining situation. But I also wanted to talk a little bit more about what we see in nature that mimics that, not intentionally, but just because of the kinds of abiotic and biotic features that exist. So let me scroll down to the next page here. Next slide. Let me move myself around so I'm out of the way. There we go. I guess that works. All right. So ecosystems that surround mines are oftentimes adversely affected by the tailings and the spoil piles, if you remember me talking about what those were yesterday in class, right? The leftovers. Many of the copper minerals or the other types of minerals, the carbonates, the sulfur, whatever else might be within the bedrock, oftentimes they contain sulfur. I think I just mentioned that, but that's a really, really common, very evenly dispersed mineral that exists in many places in the world and that exists usually kind of in the top layers of bedrock and even in the soil. Well, as precipitation falls, either through rain or snow, onto those tailings, onto those piles, the water is going to seep down through those little pieces of rock. And there are species of sulfur loving bacteria that exist within the Earth's crust. They, as well as water and oxygen, all react together to create sulfuric acid, H2SO4, sulfuric acid. It's a naturally derived compound with an incredibly low pH. And something that's kind of interesting to note about the relationship between pH and metals, as the pH drops in a solution, as it becomes more acidic, that allows metals to be more easily dissolved into that solution. And so things like arsenic, cadmium, iron, copper, or other types of metals that are in the soil, as the sulfuric acid builds up over time because of the precipitation, the acid loving bacteria, and the oxygen coming together, then we get these really, really, really high levels of metals that also become part of the solution. So if this is a river or a lake and metals are leaching into the water because of those lower acidic conditions, that can be quite dangerous. High levels of any type of metal can become toxic to aquatic life, to plants, to fish, to people, to animals that drink the water that come along the shoreline. And so that can be quite dangerous. The sulfuric acid solution that is leaching all of those metals out, that's what we call acid mine drainage. And so we talked about that a little bit yesterday, but I wanted to go back and emphasize how that travels to nearby streams, ponds, lakes, and even can percolate down into groundwater, which changes the pH of the water and can be very dangerous because it's incredibly corrosive due to that high acidity. It can cause tissue damage, and it can lead to the death of many different plant and animal species that are surrounding the mine. And so, something else to consider though, because that sounds pretty much like, okay, it's just automatic death and terrible things surrounding any type of mine. Well, yeah, I mean that definitely can happen, and I don't think we're in a great situation in that picture on the right side of the screen. However, all is not lost. Depending on where this takes place, the bedrock, the surrounding area of bedrock that hasn't been mined, that hasn't been destroyed, depending on what it's made out of, it might actually be able to act as a natural buffer to all of this low pH solution that is inundating the area. For example, limestone. Limestone, going back far enough into history, is often derived from marine organisms that died, sunk down to the bottom of the ocean, and became cemented and compacted into rock. Limestone is made of calcium carbonate. And as calcium carbonate dissolves in an acidic solution, it gives off really high levels of hydroxide. And you're kind of going, all right, I didn't take chemistry, or I kind of skipped that lesson. I don't know what you're saying. I can't really follow this. But suffice it to say that depending on the bedrock of the area where acid mine drainage is occurring, there might be some ability for the landscape itself to neutralize the acidity in those waters. And this can make it a little bit less acidic. It's probably not going to bring it back to, a pH of 7, 7.5, or 8, or whatever it was before the acid mine drainage took place. But it can sometimes be the difference between life and death in these aquatic ecosystems. So if the water, this is kind of interesting, if the water can be brought back somewhat to neutral, or even a little bit into the basic territory, depending on the bedrock, depending on what's there, depending on the ability of the land to neutralize the acids from that mine waste, if it can come back to being sufficiently basic or alkaline, then the metals that are in the water that have been dissolved because it's acidic, they precipitate back out. And so all of a sudden you get these little flecks of iron, these little flecks of copper, sometimes even little flecks of gold or other types of precious metals that will sink down to the bottom of these rivers, lakes, ponds, and be now available for us to come back in, to scoop back out, and to use. So this is kind of an interesting idea, because what it means is that in the ecosystems, there's all these little chemical changes that are naturally going to take place. And we have been observing this long enough to be able to go, I wonder if all of that waste that we have in our minds, is there a way for us to be able to go in and kind of recollect some of the metals that otherwise would have just kind of gotten washed out into wherever downstream away from the mine? So not only can we maybe improve the quality of the water, but possibly we can get back a little bit of mineral that we lost in the process of mining and excavation. So there's an interesting kind of dynamic happening there. But before I talk about that and how we can apply it to this little activity, I wanted also to go back one more time to look at this little image on the right. When we have a situation with acid mine drainage, even if the bedrock can naturally raise the pH enough for those metals to precipitate back out and become solid in the water again, that is not necessarily a good thing, because bottom feeding animals that are eating out of the sediment or collecting little bits of food at the bottom of the river, at the bottom of the lake, they oftentimes will ingest those metals, not necessarily on purpose. Just they're so small, they get mixed in with the little bits of algae that they're eating or the little bits of waste that they're eating, little shrimp or catfish or whatever bottom feeding organisms. And so then those metals become part of their body. Metals can be neurotoxins. They can really damage the brain, the nervous system, the reproductive system, endocrine system. They can kind of wreak havoc. And so if the metals that are absorbed into the bodies of those little bottom feeders, when those bottom feeders are eaten by other fish that are maybe in the top layers of the water, or by people that are fishing from that area, or animals that are catching fish out of a pond or a river, a crocodile, whatever, then those same metals can build up within the bodies of those consumers, and the whole food web in that area can be affected. We saw this we see this repeatedly, kind of routinely, with birds in the top layer, in the top levels of their food chain. Fish in these areas, the fish have pretty high levels of toxins within them, pretty high levels of that toxic metal. But then by the time it gets to the bird, they're accumulated so much that the eggshells sometimes are not fully developed, and the birds will die, or their eggs do not hatch. And it's just not really a great thing for an ecosystem. Okay, so enough on that. Let's talk about how we can recover some of those lost minerals using all of the same kind of idea. All right. So I mentioned earlier that in natural systems, sulfur-loving bacteria can produce sulfuric acid. If there's enough oxygen, if there's enough water through precipitation kind of percolating down into the soil, any of these little acidophiles, as we call them, any of these acid-loving bacteria, they will gravitate to those, and they'll end up producing H2SO4, which is sulfuric acid. So we come along and we're like, hey, we're going to basically act like those little critters because we want to have more opportunity to recover some of these lost minerals. So you take your azurite, you take the rock, you crush it up, you pulverize it till it's basically the consistency of soil, kind of broken down little bits of sediments. And then you're going to introduce it to sulfuric acid. In this case, it sort of depends on the concentration of the sulfuric acid, how fast this reaction is going to occur. So after school yesterday, I took 2 molar sulfuric acid, which Dr. R was kind enough to prepare for me through her amazing chemistry experience. And I basically I'll show you the picture. So I took a test tube and I filled it with just a couple of grams of the pulverized azurite rock. And then I poured in, I think it was about 6 milliliters or so of 2 molar sulfuric acid. This here is the actual chemical equation of what's happening. So what we get, the azurite, is that Cu3, CO3, 2, OH2, that is just the compound. That's what we see within the rock itself. We don't want the carbonate, we don't want the hydroxide, we just want the copper. And so by introducing it to sulfuric acid, which bubbles and fizzes when you first pour it in, it creates the byproducts carbon dioxide, which is the fizz, and water, but also copper sulfate. So now we've moved the copper from the rock into this new compound called copper sulfate, which is a liquid. So because the pH is so low, just like we saw in nature, because the pH is really low, the metal is able to be dissolved into and become part of the solution. So now we have this weird little like funky green colored liquid. And you're like, okay, well, that doesn't really look like anything that you would want if you were mining. And you're right. First, we have to remove it from the rock, but now it's a solution. We want the solid. We want that shiny, pretty copper that we can use to produce whatever it is that we want to produce out of that mineral. And so what we're going to have to do is figure out a way for us to get that metal to become a solid again. Now, in nature, we might do this through the addition of crushed limestone, right? We might do this through just that slow percolation of that sulfuric acid, copper sulfate. I'm sorry. As that filters through the ecosystem, we will see that naturally occur. But we don't want to do that. We want to do something else. We want to get it straight out into this solid metal form. And so here's what's going to happen. What we need to do is first separate out solid from liquid. So you just pour it through a filter. And when it gets to the bottom, it has kind of that characteristic blue, sort of aquamarine color. It's quite pretty. So I filmed myself doing this after school yesterday, and it's kind of shaky and a little bit noisy. So sorry for that. But you can see the liquid, you can see the solution going through the filter paper. And just along the side, you can see how pretty blue. It looks kind of like tropical ocean water. So that is the copper sulfate that's coming out of the filter. And what is it doing now? It's hitting a nail. Well, that's weird. Why did I put a nail in there? Let me show you. Instead of trying to raise the pH and have the metal precipitate out, what we can do is actually add iron. Let me move myself out of the way again. Over here, I guess, is probably better. So iron, interestingly enough, when it's added to copper sulfate, the copper will precipitate out. It forms a solid. We call it, we can see it here in this little chemical equation. So copper sulfate, which is the blue stuff, the blue liquid, whenever you just drip it onto the surface of iron, it becomes copper plated. The copper comes right out of the solution and directly plates onto the iron. So you've got iron sulfate, which is left behind in the solution, the liquid part, and then just legit straight copper, which is what we're trying to get in this whole process. So let me show you this video again because it's kind of cool. If you look really, really closely at the nail, which represents the iron, it's a galvanized iron nail. I had to sand it a little bit to get the protective coating off, but it's made out of iron. And that is important because iron's really strong. And if you combine iron and copper together, you get a really, really nice metal alloy where you've got excellent conductive nature of copper, but with the strength, the tensile strength and the durability and the inability to corrode through the iron. So you have a really, really strong metal. And you can kind of see as it's dripping down the side there. I moved my camera around to try to get a better angle, but you can see on the side of the nail, the copper, that bright copper color. It's kind of that orangish, coppery color. How else do you describe copper besides just saying copper? I don't know how to do that. Here's a better look. So by the time I was done, I ended up taking a pipette of the copper sulfate of the iron sulfate and just gently dripping it down onto the surface of the nail in any place that it wasn't already coated. That's a different nail. That's an iron nail on the left and the comparison of the copper plated nail on the right. So now what we could do is if we wanted, we could melt the two and separate. So we have just pure iron and just pure copper, but iron copper as an alloy together does have its own uses. It's pretty strong. In fact, I have a little note about that down here. There might be times when iron is added intentionally to copper for positive benefits. You've got the strength of the iron and the corrosion resistance, but you still have that really high conductivity of the copper. So it makes a really great product at the end. There's only one last piece to all of this, and that is what's still in the test tube. And that is a really, really nasty low pH, highly acidic leftover. And this is still the problem in nature as well. Not only does the metal precipitate out and potentially cause problems by being able to move up the food chain and cause contamination that way, but you still have some residual acid mine drainage. You still have that low acidity. And if we're using the process of adding iron to this on site or in another location, then we have leftovers now that we have to deal with. What are you going to do with gallons and gallons of this iron sulfate, which has a pH of less than 4? You can't just dump it out. You can't, simply put it in the backyard and dump it down the sink, you're going to have to dilute it. You're going to have to raise the pH to make it safe again before you can dump it out as wastewater. So this was a really long explanation, but I hope that it kind of helps walk you through what's happening with mining, this whole complication of acid mine drainage, and how we can kind of have some limited natural ways to neutralize it depending on the bedrock. Calcium carbonate or limestone is a great asset if you have a mine because it's going to reduce a little bit of the acid mine drainage that will naturally occur over time. But we also have found a way to make that work for us. If we can be better at recovering lost metals when we're removing them through our own processes by adding sulfuric acid and then, plating out things like copper, even though we're going to be left with that really concentrated leftover low pH solution, we have now recovered a lot more of the metal. And so the tailings and the spoils, the leftovers on site, will have less of that metal within it and be less of a problem in the future. So it's not a perfect solution, but it definitely makes us think a lot more about the benefits and the drawbacks of using different techniques within mining. So I hope that that was helpful. I appreciate you walking through all of this. And that's it for today.